Hi, today I'm gonna talk about the Zariski topology. So let me make a short recap. So let A be a ring, and last time we defined the spectrum of the ring to be the set of prime ideals of the ring A. And now let's take a subset of the ring, and we define the vanishing set of this subset to be the prime ideals in the spectrum, which contain M. So this is a subset. Let me write it later. This is a subset of the spectrum, which is so maybe let me write it like this, but this is the set where f of p is 0 for all f in M, where f of p is the class of f in A mod p. So I gave last time this motivation that we see the elements of this subset A as functions and the prime ideals as points. Okay, and this whole thing lives in the spectrum. And the claim is now that these sets V of M for subsets of the ring A define the closed sets of a topology. So for M subset A, sets of a topology on spec A. And let me make a short remark. So it's easy to prove that we can replace subsets M by ideals. So by arbitrary ideals, because we can always take, so this vanishing of M is always equal to the vanishing of the ideal generated by M. Okay, now let's prove this. So at first we note that the whole space is closed. So this is the set such that the 0 ideal is contained in P, and that's certainly true for all prime ideals. So that's the whole space, spec A. Then let's look at V of A, which is a set of prime ideals such that A is a subset of the prime ideals. That's clearly the empty set. So we have that these two sets are closed. Next claim is that the intersection of closed sets is closed. And how do we prove this? Well, we prove that V of, so the vanishing of a union of sets is equal to the intersection of the vanishing. And this, so we have a intersection of closed sets, and this then proves that it's closed again. So let's prove this. So let's take a prime ideal in here. Well, it's in here if and only if. So these are just some elementary operations. So that's the definition. Well, and then that is the case if and only if all these mi's are contained in P, and that's the case if and only if P is in these vanishing sets, and well, that's the intersection. So P is in the intersection of these vanishing sets. Okay, so what do we have now? So we have the whole space is closed, the empty set is closed, the intersection of closed set is closed, so we need that finite unions of closed sets are closed. So show this, we show that V of the set M times N is V of M union V of N. And similarly as before, this shows the claim that the union of two closed sets is closed. Okay, so let's first prove one inclusion, so namely let's prove this inclusion. So if P is in here, then it's quite clear how it follows. So this means that M is a subset of P, or N is a subset of P, and then clearly, so P is an ideal, so also M times N is a subset of P, and P is in here. So here we just use that P is an ideal. We don't even need that it's prime. Okay, and now let's prove the other inclusion. So that's the only thing where we have to do a little more, but not too much. So let's say P is in here. That's, well, clearly the case if and only if M times M is a subset of P. And now we assume, without loss of generality, that M is no subset of P. If it was, we would be already finished, because then P would be in the vanishing of M. Oh, I wanted to say, we suppose that M is no subset of P. Okay, and now let's pick a M which is not in P. So M should of course be in M. And now, well, that doesn't follow from picking this, but M times N is definitely in P for all N in N, because, well, M times N is a subset of P. And as M is no subset and P is a prime ideal, we get that N is in P for all N in N. And then we get that P, so this means that N is a subset of P, so P is in V of N, and then it's in, so we have picked something from the left-hand side. Now we get that it's in the right-hand side. Okay, and let me make a short remark. So here I meant with M times N just the set theoretical product, not the ideal generated by this, as I suppose that M and N are just sets. But of course one could also make this similarly. If we would assume that M and N are ideals, we would take the ideal generated by this. But it doesn't change anything, as V of such a product is the same as I mentioned, as V of a subset M is the same as V of the ideal generated by M. Okay, so we are already done with this. We have shown that we get a topological space. And, well, the next goal is to define affine schemes. So affine schemes are, well, the category of affine schemes is equivalent to the category of rings, but we have to do a little bit more. So I'm not sure what we'll be doing in the next video. Maybe a little bit about sheaves, or maybe I'll go directly to definition of ringed spaces and locally ringed spaces, and the structure sheaf of the spectrum. But yeah, we'll come to that. Okay, so That's it for that video. Have a good day and bye.